So, we've got to talk about one of the biggest, maybe the biggest challenge in tech right now. How do we stop these incredibly powerful AI models from being used for bad stuff? We're going to dig into some really cool new research from Google DeepMind that has a pretty wild solution. What if you could build a security guard that lives inside the AI's brain? Okay, let's dive in. I mean, really, this is the question that probably keeps a lot of AI developers up at night. You've got these models getting more and more powerful, and the risk that someone could turn them into, a super weapon for cyber attacks, that risk is growing every single day. And look, this isn't some far-off sci-fi movie plot. It's a real problem that the big AI labs are trying to solve right now. So the big question is, how do you police a system that might just be smarter than you are? All right, so here's how we're going to tackle this. First, we'll get into this whole idea of an AI security guard. Then we're going to go inside the AI's mind to see how they actually work. After that, we'll check out the new breakthroughs that are making them way smarter. And we'll wrap up by looking at the constant cat and mouse game that is AI safety. Okay, Section 1, the AI security guard. This is all about the challenge of trying to monitor a system that's, well, potentially super intelligent. And just to be super clear here, this is not a problem for tomorrow. The Google researchers are really hammering this point home. These frontier models are already powerful enough to, and this is their word, supercharge what malicious users can do. It's exactly why every major AI lab has some kind of safety filter trying to catch these bad requests before the AI even sees them. So when it comes to playing security guard, there are basically two main approaches. The first one is kind of brute force. You get another giant powerful AI to watch over the first one. I mean, it works, but it is wildly expensive. We're talking about basically doubling the cost of every single question you ask it. The other option, which is way more elegant, is what we're talking about today. It's a tiny, super efficient little monitor called an activation probe, and it literally lives inside the AI's brain. And I really want you to get this, because this is the breakthrough. We're talking more than 10,000 times cheaper. Let that sink in. These new probes from Google are over 10,000 times less expensive than using a whole other language model as a monitor. And they get similar, sometimes even better, results. So this isn't just some minor improvement. This is what actually makes real-time protection possible at scale. It's a game changer.
All right, Section 2, inside the AI's mind. So how do these probes actually watch an AI's thoughts? Let's get into the nuts and bolts.
Okay, the best way to think about an activation probe is it's a tiny little detective, a specialist. Its one and only job is to spot suspicious patterns. And here's the cool part. It's not reading the words you type in. Instead, it's watching the internal signals, the activations that are firing between the neurons inside the big AI as it's processing your request. It's looking for the electronic fingerprint of bad intent. Okay, now I know this diagram looks a little intense, but the idea behind it is actually pretty simple. The probe is basically eavesdropping on the data flowing through the main AI. Those are the activations we were talking about. It grabs all that super complex information, shoves it through its own tiny little neural network, and then, this is the key, it boils everything down to one single number, a score that basically says, is this request dangerous or not? You don't need to worry about the specific formulas, just that core idea. It takes all this complexity and turns it into a simple thumbs up or thumbs down. So let's just walk through that one more time. Step 1, for every single part of your prompt, every word, every token, the probe grabs or harvests that internal data. Step 2, it transforms that data using its little network. Step 3, it combines or aggregates everything into one big picture. And finally, Step 4, it spits out that final score. It's a really smart, really efficient system. But there was a big catch, a major blind spot. And this is the catch right here, straight from the researchers themselves. They say probes are indeed a cost-effective misused mitigation, but there is a key problem. They are also fragile to distribution shifts. What that basically means is these probes are great at spotting the kinds of trouble they were trained to see. But what happens when the attacker throws them a curveball, something they've never seen before? And that curveball led to a huge blind spot. Imagine trying to find a needle in a haystack. An attacker could hide one single malicious instruction inside a giant wall of perfectly normal text, like burying one bad line of code in thousands of good ones. The probe would just get overwhelmed. The bad signal got completely drowned out by all the good signals, and the attack would sail right on through. This is what the researchers call the long context problem. Okay, on to Section 3, a smarter breed of probe. So this long context problem was a big deal. How did the Google DeepMind team get around it? Well, this is where things get really clever. They came at this with a three-pronged attack. First, they came up with better architectures, new designs for the probes themselves that were way better at finding that needle in the haystack. Second, and this is pretty meta, they used another AI, something called Alpha Evolve, to automatically search for and discover even better probe designs. So you've got an AI building a better security guard. And third, they built this really smart hybrid system they call a cascading classifier. And this cascading classifier idea is, frankly, brilliant. Think of it like a triage system at a hospital. The cheap, super fast probe acts like the first-line nurse. It handles almost everything, the easy cases. But if it gets a request that's kind of in a gray area, where it's not totally sure if it's safe or not, it doesn't guess. Instead, it cascades it up the chain to the expensive, powerful specialist, the big LLM monitor, for a final verdict. So the whole workflow is just really smart and efficient. The probe takes the first look. If it's obviously fine or obviously bad, boom, decision made, cheap and fast. But if it's in that murky middle ground, it punts the decision to the expert. It really does give you the best of both worlds. You get the incredible speed and efficiency of the probe with the raw power and accuracy of the big LLM as a backup. And you don't have to take my word for it, the numbers are right here. This chart is pretty amazing. It shows that this new cascade system, it actually makes fewer mistakes than just using the big, powerful language model by itself. And it does that while costing about 1/50th of the price. I mean, come on, it is literally better and cheaper. That's just a massive, massive win for AI safety. So that's it, right? Problem solved, we can all go home? Well, not so fast. Welcome to our final section, the cat and mouse game. Because in security, for every new lock, someone is already designing a new lockpick. Look, it is really important to be realistic here. These new probes are a huge leap forward, no doubt. But they are not a magic silver bullet. The researchers are very upfront about this. The most sophisticated jailbreak attacks, and these are really clever tricks designed specifically to fool safety systems, they can still get past even this new, shiny defense. And this table tells a pretty sobering story. When you're up against what they call adaptive attacks, that means the attacker knows what kind of security you have in place and is actively trying to beat it, the success rate for jailbreaks is still over 20%. That's for both the big fancy LLM and the best new probe. Let's be real, that means about 1 out of every 5 of these advanced attacks is still slipping through the cracks. The paper really puts it bluntly. We are a long way from adversarial robustness in this domain. And that's just a stark, honest reminder that this is a ridiculously hard problem to solve. The job is nowhere near finished. But I don't want to end on a down note because this is what this all means today. This isn't just some dusty academic paper. This work, these breakthroughs, have been put directly into action. These very same misuse probes are running in production right now inside Google's Gemini models that people are using every day. This is what it looks like when safety research makes a real, tangible impact. And that leaves us with one final big question to think about. We've just seen how AI safety tools are getting seriously smart, right? But it forces us to ask, as our security guards get smarter, are the methods for breaking in getting smarter even faster?